In cosmology, the cosmological constant, usually denoted by the Greek capital letter lambda, alternatively called Einstein's cosmological constant, is a coefficient that Albert Einstein initially added to his field equations of general relativity. He later removed it. However, much later it was revived to express the energy density of space or vacuum energy that arises in quantum mechanics. It is closely associated with the concept of dark energy. Einstein introduced the constant in 1917 to counterbalance the effect of gravity and achieve a static universe, which was then assumed. Einstein's cosmological constant was abandoned after Edwin Hubble confirmed that the universe was expanding. From the 1930s until the late 1990s, most physicists agreed with Einstein's choice of setting the cosmological constant to zero. That changed with the discovery in 1998 that the expansion of the universe is accelerating, implying that the cosmological constant may have a positive value. Since the 1990s, studies have shown that, assuming the cosmological principle, around 68% of the mass energy density of the universe can be attributed to dark energy. The cosmological constant is the simplest possible explanation for dark energy and is used in the standard model of cosmology known as the lambda CDM model. According to quantum field theory, which underlies modern particle physics, empty space is defined by the vacuum state, which is composed of a collection of quantum fields. All these quantum fields exhibit fluctuations in their ground state, lowest energy density, arising from the zero-point energy existing everywhere in space. These zero-point fluctuations should contribute to the cosmological constant, but actual calculations give rise to an enormous vacuum energy. The discrepancy between theorized vacuum energy from quantum field theory and observed vacuum energy from cosmology is a source of major contention, with the values predicted exceeding observation by some 120 orders of magnitude, a discrepancy that has been called the worst theoretical prediction in the history of physics. This issue is called the cosmological constant problem, and it is one of the greatest mysteries in science, with many physicists believing that the vacuum holds the key to a full understanding of nature. The cosmological constant was originally introduced in Einstein's 1917 paper entitled The Cosmological Considerations in the General Theory of Reality. Einstein included the cosmological constant as a term in his field equations for general relativity because he was dissatisfied that otherwise his equations did not allow for a static universe. Gravity would cause a universe that was initially non-expanding to contract. To counteract this possibility, Einstein added the cosmological constant. However, Einstein was not happy about adding this cosmological term. He later stated that, "Since I introduced this term, I had always a bad conscience. I am unable to believe that such an ugly thing is actually realized in nature." Einstein's static universe is unstable against matter density perturbations. Furthermore, without the cosmological constant, Einstein could have found the expansion of the universe before Hubble's observations. In 1929, not long after Einstein developed his static theory, observations by Edwin Hubble indicated that the universe appears to be expanding. This was consistent with a cosmological solution to the original general relativity equations that had been found by the mathematician Alexander Friedmann, working on the Einstein equations of general relativity. Einstein reportedly referred to his failure to accept the validation of his equations, when they had predicted the expansion of the universe in theory, before it was demonstrated in observation of the cosmological redshift, as his biggest blunder. According to George Gamow, it transpired that adding the cosmological constant to Einstein's equations does not lead to a static universe at equilibrium because the equilibrium is unstable. If the universe expands slightly, then the expansion releases vacuum energy, which causes yet more expansion. Likewise, a universe that contracts slightly will continue contracting. However, the cosmological constant remained a subject of theoretical and empirical interest. Empirically, the cosmological data of recent decades strongly suggests that our universe has a positive cosmological constant. The explanation of this small but positive value is a remaining theoretical challenge, the so-called cosmological constant problem. Some early generalizations of Einstein's gravitational theory, known as classical unified field theories, either introduced a cosmological constant on theoretical grounds, or found that it arose naturally from the mathematics. For example, Arthur Eddington claimed that the cosmological constant version of the vacuum field equation expressed the epistemological property that the universe is self-gauging, and Erwin Schrödinger's pure affine theory, using a simple variational principle, produced the field equation with a cosmological term. In the 1990s, Saul Perlmutter at Lawrence Berkeley National Laboratory, Brian Schmidt of the Australian National University, and Adam Rees of the Space Telescope Science Institute were searching for type Ia supernovas. By that time, they expected to observe the deceleration of the supernovas caused by the gravitational attraction of mass according to Einstein's gravitational theory. The first reports published in July 1997 from the Supernova Cosmology Project used the supernova observation to support such deceleration hypothesis. But soon they found that supernovas were flying away in an accelerating manner. In 1998, both teams announced this surprising result. It implied the universe is under accelerating expansion. The cosmological constant is needed to explain such acceleration. After this discovery, the cosmological constant was put back into the equation of general relativity. The mystery of the cosmological constant continues to challenge our understanding of the universe. But one thing is certain: it is a key component in the ever-evolving story of cosmology. The story of the cosmological constant takes an even more intriguing turn when we dive into the realm of quantum field theory. Here lies one of the most perplexing unsolved problems in physics. Why doesn't the zero-point energy of the quantum vacuum lead to an enormous cosmological constant? What mechanism cancels it out? Most quantum field theories predict an enormous value for the quantum vacuum energy. If we assume that the quantum vacuum is equivalent to the cosmological constant, a concept still debated among physicists, then we face a staggering discrepancy. Dimensional analysis and effective field theory suggest that the universe, if described by an effective local quantum field theory down to the Planck scale, should have a cosmological constant of the order of the Planck length squared. However, the measured cosmological constant is smaller than this theoretical prediction by a factor of about 10 circumflex 120, a difference so vast that it has been labeled the worst theoretical prediction in the history of physics. To complicate matters further, some supersymmetric theories require a cosmological constant of exactly 0. This adds another layer of fine-tuning to an already intricate puzzle. Particle physics offers no known natural way to derive the tiny cosmological constant observed in our universe. Even within the framework of string theory, no vacuum state in the landscape of possible solutions supports a metastable positive cosmological constant. In 2018, a group of physicists proposed a controversial conjecture that would imply no such universe can exist. In 1987, physicist Steven Weinberg proposed a compelling idea based on the Anthropic Principle. According to this principle, the value of the cosmological constant is not just a random number, but is finely tuned to allow for the existence of life. Weinberg suggested that if the vacuum energy had different values in different regions of the universe, then observers, like us, would only exist in regions where the vacuum energy is just right to support life. Imagine a universe where the vacuum energy is negative and significantly larger than what we observe. Such a universe would be closed, with a lifetime too short for intelligent life to develop. On the flip side, a universe with a large positive cosmological constant would expand too rapidly, preventing the formation of galaxies and, consequently, life as we know it. Weinberg's argument implies that the domains where the vacuum energy is compatible with life are exceptionally rare. Using this reasoning, he predicted that the cosmological constant would be less than 100 times the currently accepted value, a prediction that has held up remarkably well over time. In 1992, Weinberg refined his prediction, suggesting that the cosmological constant would be between 5 to 10 times the matter density. This argument hinges on the assumption that vacuum energy density remains constant throughout spacetime, a condition expected if dark energy is indeed the cosmological constant. But what if the vacuum energy varies? Some theories propose that it could be the potential of a scalar field, like the residual inflaton, or even a form of quintessence. Another intriguing approach is the multiverse theory, which posits the existence of numerous parallel universes, each with different physical laws and fundamental constants. According to the Anthropic Principle, we naturally find ourselves in one of the rare universes where conditions are just right for intelligent life. However, this explanation has its critics, who argue that it falls into the trap of the inverse gambler's fallacy. In 1995, physicist Alexander Vilenkin refined Weinberg's argument further, predicting a cosmological constant value that was only 10 times the matter density, roughly 3 times the current value as determined. As we ponder these theories, one thing becomes clear. The quest to understand the cosmological constant is not just a scientific journey, but also a philosophical one. It challenges our understanding of the universe and our place within it, urging us to explore the boundaries of both physics and philosophy. Join us next time as we delve deeper into the mysteries of the cosmos.